Okay guys, so today we're going to do an exam question 6 of exam, the second semester's exam 2018. You can have a look at that. So with this question, it deals with pumps in series, pumps in parallel, and just a single pump. Alright, so first of all, let's start with the question, what does it give us? So water must be pumped from one reservoir to another. It reads, the piping system which is used has a system head relationship of H is equals to 17.5 plus 12,500 times Q squared, with H the head in meters and Q the discharge in meters cubed per second. So that tells you, I'm telling you there that the units for the system head relationship, I'm telling you the units for H and Q. So you need to make sure that the values that you're going to substitute in this case, which will be Q and H, are in fact in those units, especially Q in this case, which should be in meters cubed per second. So if we go on further, it tells us a pump has the following characteristics. So here they give us H, and they give us Q, and they give us N efficiency. So, but the one that we'll have to convert, here we see H is in meters, which is fine. Q, however, the unit for it is in meters cubed per hour, so we cannot use this. We'll have to convert to meters cubed per second. So the efficiency then throughout is 0, 66, 81, 73, 55, and 31. So that stays the same. However, we'll see what happens to those later on. So then further on it reads, determine graphically. So that will mean that you'll have to use graph paper, the discharge, the pressure head, and efficiency, and thereafter the power required. So you'll have to read off the discharge, you'll have to read off the pressure head H, and the efficiency, and thereafter calculate the power required. So we've been given about 1, 2, 3, 4, 5, 6, 7 columns of data, including the labels. So you'll have to start by drawing up a table for yourself, like we have done here. So you'll draw a table for your system curve, where you're going to use this formula here. And further on, if we go on, we'll see that they tell us we have to determine the discharge, the pressure, the efficiency, and the power required if one pump is used, 6.1, if two pumps are used in parallel, and two pumps used in series. So you're going to have 3 questions where you're going to have tables drawn. We have one pump, parallel pumps, and series pumps. So in the first one, you'll see I started with the system curve. So that's the first one that you'll have to do. So let's go and rewrite on our script or on your piece of paper, rewrite the H values that you need here. Okay, so let's do that. So the first one for Q, the first Q value in meters cubed per second, we'll have to convert. It's going to still be 0. Let's do the second one where it reads 54. So we'll have to convert that. How do we convert it? We'll simply take the 54 divided by 3,600. Where does this come from? It comes from the 60 times 60 seconds in a minute and 60 minutes in 1 hour. That's why we have this as 3,600, and that will give you the unit meters cubed per second. So let's do that for all of the values we've been given. Now we're good. So now we can go and substitute these values that we've calculated just now. We can go and substitute them into this guy. Okay. Alright, so now we're good. Now we've already got our H system, so we can plot that if you don't know what to do next. So then at least you can plot this so long on your graph paper and get some marks for this. And then the next part would be just to simply rewrite the values you've been given, except this time your Q values have to be the ones you calculated here. So okay, so now we've got the values converted, we've got our H system curve that we'll be able to plot. So now we can do the parallel. For parallel pumps, we know that the rule says for parallel pumps, we'll have to multiply the Q values by 2. And for pumps in series, we know that we'll have to multiply the H values by 2. Okay, so we're going to use this here. The values from the pump characteristic curves to do question 6.2 and 6.3. So let's do this one. So again here for parallel, that will be 75, 65, 57, 47, 34 and 19. And the only stuff we need to multiply by 2 is these values here. So the first one will be 0. Okay, and the next one will be obviously 0.030. The next one will be 0.050. The next one will be 0.070. Next one 0.090. And the next one would be 0.110. So that's pretty simple and easy. Then the next one would be pumps in series. So here again we have to multiply the H values with 2. So we'll take the 75 times 2. That's what we'll do here. Okay, so that becomes what? It's 75 times 2 gives us 150. 65 times 2 gives us 130. 57 times 2 gives us 114. 47 times 2 gives us 94. 34 times 2 gives us 68. 19 times 2 gives us 38. Okay, so the Q values stay the same. So we'll use these Q values. So it becomes 0, 0.15, just another 0 there, 0.025, 0.035, 0.045, and 0.055. Okay, so now we're ready to plot. Okay, so now we've calculated our values for one pump, for 2 pumps in parallel, and 2 pumps in series. So these values we need to go and plot now. So we need to plot our H system curve, which will be this one. So we need to plot this one, our H system curve. We need to plot this one. And we need to plot this one. And we need to plot this one. Okay, so how do we determine how are we going to plot our data? So first of all, we need to look at what are the maximum values from the data. So first of all, let's look so normally where you would find your maximum Q value, let's start with the Q values. So Q max, the maximum Q value will be found where you have your parallel pumps. Because remember, here you multiply Q with 2. So this is where you'll find your maximum Q value that you will have to plot on your graph paper. So in this case, the maximum Q value here is 0.110. 0.110 meters cubed per second. Okay, then let's find our maximum H value, for example. So our H max, will be where we've multiplied our H values with 2. So that's where we'll find the maximum value for H, where we have 2 pumps in series. So if we look at the H values, the maximum value here is the 150. So we'll use 150 meters as our maximum value there. And then lastly, we need to also look at the efficiency, because we also need to plot efficiency. So the first one, the Q max, will plot on the horizontal axis, and the H max will plot on the vertical axis on the left hand side, and our maximum efficiency, which we can find from the data given. Let's look at that. What is the maximum efficiency given? That has been given as 81. This one here, 81%. That's our maximum value for efficiency. So let's jot that down and tell ourselves that it's 80%. So we're going to have to fit those 3 maximum values on our graph paper. So if we can adjust our screen so we have our data, now we can start plotting. So let's take our graph paper and let's start plotting. So this is normally the graph paper that you will be given. So you'll see you'll have to count the blocks so that you can determine what is the best way to fit your data. So let's start by taking our Q values that we've looked at in the previous page. So let's start with the Onepump. Let's start with plotting our data for Onepump. So let's pick a color for that. Remember, you can use any color except red and green. So for this purpose, I'm going to plot the Onepump pump characteristic. Let's say we're going to use a green or lime green, or let's rather use, yes, lime green. Lime green is fine. So we're going to plot this first. The pump characteristic for Onepump, or the values for Onepump, are H and Q values. Okay, so the first one is going to be 0/75. Okay, so let's go to our graph paper and see if we can start doing that. Alright, so we can't really start just yet because we know we need to look at the maximum values. So what you can do is, normally what you do is, you would start by selecting the axis. So we know that Q has a maximum of 0.011. So therefore we could use the lower axis, the lower horizontal axis of the graph paper to plot our values. So you can check that by counting the blocks. So here you have one block, a second block, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So I have enough blocks. So I can start with 0 at the bottom and with my first value being 0.01, 0.02, 0.03, 0.04, 0.05, 0.06, 0.07, 0.08, 0.09, 0.010, 0.11, 0.12, and so on. So we have enough values there for our Q values. Let's give it a name, being Q discharge, and a unit, meters cube per second. Okay, and we'll plot our H values on the left hand side. So we'll plot our H values with its unit in meters, and we can safely see that we have about 1, 2, 3, 4, 5. We have enough blocks. If we scroll up, we'll see we have more than 16 blocks or more than 15 blocks, so we'll be able to use a scale of 10. So that's 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, 110, 120, 130, 140, 150, 160, and 170. Remember, our maximum value is only 150. So we should be okay up to here, up to 170. Then we also need to plot the efficiency. So therefore we need another axis. So you'll choose the right hand side for your efficiency. Okay, so then you need to measure, so then you need to write down your efficiency, or plot your efficiency values rather, in percentage. So we'll see that we'll easily fit. Our maximum is 80, so we know that we have more than 16 blocks, so we can use 2 blocks for 10% to represent 10%. Next one being 20%, next one 30%, that one 40%, next one 50, 60, 70, 80, 90% here, and 100% here. Alright, so let's check our axis whether it's correct. We've got 10, 20, 30, 40, 50, 60, 70, 80, 90, and 100. So we're good to go. Now we can simply start plotting our values. So let's start with the first one being, if we go back to our previous page. So let's pick a color. Let's do the H system. Let's do it in the lime green color. So let's do this one in lime for H system. This guy here. Let's plot all of these values. So if we plot the H system, it's clear that at 0 we have a head value of 17.5. So that will be more or less somewhere here. Then our next point would be at 0.015. So that will lie here. We'll start there somewhere, and it will move all the way up to 20.313. So that will lie somewhere there. Then our next point would be at 0.025. Remember, you're plotting against the Q values. You're plotting against these Q values. So the next one would be at 0.025, which is on this line here. On this line here. So let's move all the way up and let's go to 25.3. 25.3. So that's that point there. Then our next point is 0.035. That one will be here. Let's move all the way up to our head value that we have to plot, which would be 32.8. So it's almost 33, which would be somewhere there. Our next point would be 0.045, which will lie on this line here, and we'll go all the way up to 42.8. 42.8, which should be somewhere right there. Then our next point would be 0.055, which is on this line. Let's go and let's mark it, which is 55.3. So it will lie somewhere here. And there you go. This is your H system line that you can connect. So you can connect the data points now. So that last line is a bit skewed. Not better. Let's make it better. I'll try my best here. So that looks much better. So that's our H system. You can maybe write it there so that you don't confuse yourself with the other plots. So that's your H system. Now we need to plot Onepump, the characteristics of Onepump on our graph paper. So let's do that. And let's use black. So this will be for Onepump. So our first value, discharge at 0 for Onepump. At a discharge of 0, we have a head value of 75. 75 right there. At our discharge of 0.015, we have a head value of 65. 65, which is there. Our next one being 0.025. Oh, we just need to go back. 65 is on this one here. Right there. And then 0.025, that one lies on 57, so that will lie somewhere here. That's our 57 mark. Then the next one being 0.035, which lies on 47, which should be more or less there. And our next one being 0.045, which is this line here, which will sit at 34. 34, and our last one being 0.055, which would be 19. Value of 19 right there. So now we can simply connect these values. Make sure you've got a steady hand while you're doing this. And this will be for one pump. So now you sit with a duty point here, and which you will later on use. So our first duty point value, we can clearly see from the graph, if we go and read the head value, it's gonna be more or less 40 or 39. If you plotted it accurately, you should get 39. And if we go down, our Q value should end up at 0.042. So that's our first point. But we still need efficiency, so we also need to plot efficiency. So we'll do that next. Okay, so we've plotted the H system curve and the pump characteristic curve for one pump. Okay, so let's move on. So if we go and look at our data, for pumps in parallel, this is what you will have to plot. We will have to plot 6.2, where we have our values for the pump in parallel. So let's pick a color. Let's pick, in this case, let's pick the color orange. Okay, so let's move on and let's plot these values, 6.2 for the pumps in parallel on our graph paper. So let's go on to our graph paper. So let's see, the first value reads an H value of 75 and a Q of 0. So we have 0 and 75. 0 and 75, which would sit right there. Okay, and our next value would be the one corresponding to 0.03. So remember, with the pumps in parallel, we multiplied our discharge values by, we multiplied them with 2. So our Q value here is going to be, for our second plot point, will be 0.03. So it will be on this line right here, and at the head value of 65 right here. So this is for your plot for the parallel pumps. Okay, so the next point would be our 0.05. So we'll look at 0.05. Remember, you're plotting against the discharge values. So it's this one we had, and we had this one. So you can mark it at the bottom of the axis just to use it as a reference. What you can do is you can use a ruler. Okay, so we've managed to add our ruler, so this will help us quite a bit. So let's see if we go and use our ruler to show us clearly where the value should be. This should be what you should be getting. Okay, so our first one is under the 0.03 mark. Our next one would be the 0.05. So let's move on to that one, and it has a head value of 57. So if we go and measure that, it should be around here. go and measure that. It should be around 57, should be right about there. Then we can turn off the ruler. So it's about there, 57. And our next point would be under 0.07. So it's going to be this guy here. So we don't really need a ruler here because that line is thick enough. So we'll move on to its height value for 0.07, which is 47. So that one will lie somewhere right here. That's going to be our 47. So the next point would be over our 0.11 reading. No, sorry, it's going to be 0.09. So the next reading will be our 0.09. So and that will be 34, the height value being 34. So it's going to be this one, right about there, 34. Then our last one being 0.11, which is on this line here, and that will end up, it's on this line here, and that will be 19. So that should be more or less there. Then you simply need to connect your data points as accurate as you can with a smooth line. That should suffice. So that will give you your second working point. So this will be for pumps for parallel. Parallel pumps, for the two parallel pumps. Now the second one we can do is the one where we have our pumps in series. We still need to plot the efficiency. We'll do that last. Okay, so let's do the pumps in series now. So here we had to multiply the H values, our H values. We had to multiply our H values with 2. So we had to multiply our H values with 2. Let's do that. So our first reading is going to be 150. So let's go up. And our discharge is 0. So we have to plot against discharge. Still the same. So it's going to be, the first one is going to be right here. 150 over 0. The next point is going to be 130 over the 0.15. Which is going to be right here. Okay, so it's this guy here. Our next one will be the 0.025. So that will be this point here. And the head value there is 114. So let's go up and see where should we end up. If you want to, you can use a ruler again to help yourself out. So again, we have to do the 0.025 guy. So you can place your ruler like that and then go up and see your head value should be 114. So it should be somewhere here. We have 10, there's 5, so 4, it's about there, right about there. Then we can remove our ruler. And we'll see there's our 114 mark. 114. Okay, let's do the next one. Next one being 94 meters. So let's look at our discharge value, which is 0.035. So let's go and find that one, 0.035. So it's going to be this one here. So let's use our ruler again. So there we go. Perfect. Let's go up to our head value, which is 94. So that should be somewhere about there. 94. We can remove the ruler. You can get a proper mark there, which is this one here. There we go. And our next point would be the 0.045. So let's go and find that 0.045. That should be this one here. So let's use our ruler again. So let's move it slightly. That's perfect. Okay, so there we go. So that's 0.045, and we need to look at the head value being 68. So let's go and look at that. 68. Let's pick up pen. And 68 will lie somewhere there. Let's remove our ruler. And we'll sit with 68 right there. And our last point would be over the 0.05 discharge mark. So let's go and find that one. It's going to be this one here. Let's use our ruler again. So it's going to be over this one. And we'll place our marker at 38. So 38 should be more or less right there. Then we'll remove our ruler. So we have all our plot points on our graph paper now. We can combine the points so we can get a nice curved shape. Mine's not perfect. Let's just redo it again. You need to try and get your line as smooth as possible, not wavy. So that should be more or less what it should look like. So the last thing you'll have to plot is obviously your efficiency, but let's first mark our line here. So this is for pumps in series. Let's write down this is for series, for our pumps in series. Okay, and we'll also have a working point somewhere here. Okay, so now we can simply read off these values, but we first need our efficiency plot as well. So let's do the efficiency plot quickly and then we can continue. So our first plot, we can use our ruler here. So the first one being over the 0.015. Okay, and the efficiency there is 0. No, sorry, that's 66%. 66%. And let's get a nice color here. Let's use, in my case, I'm going to use a red color. You're not allowed to use red, but you can maybe use a purple color also. So let's go and see. So you'll see this here, we have our area for plotting our efficiencies. So this is the axis for the efficiency. You won't plot your efficiencies on the right hand side of the graph. You'll plot it on the left hand side of your graph paper. This is just you have to imagine that this axis here is actually sitting on this side, ignoring all of this. So you need to imagine that this axis is actually on this side of your graph paper and use it accordingly. So let's just quickly get rid of those lines. So here we'll see that 66, here we have 60, this will be 65, and 2 more blocks, and that should give us 66. So 66 should lie somewhere here. Somewhere there. Let's remove our ruler so we can see that the efficiency is this one here. It's going to be 66, more or less there. Okay, and remember our first one that we should have had would have been the 0. Remember the first plot is 0, so the efficiency is at a discharge of 0, the efficiency is 0. So that's actually our first plot. And our second plot would be the 66% one. Okay, our next one being 81% over our second plot, which would be this one here, the 0.025. So let's use our ruler just to get an accurate measure here. Then we'll go up, and our value has to be 81%. So there's 80%. Here's our 80%, 81. Remember, it's 2 blocks, 2 small blocks, because you used 2 blocks to represent 10%. Okay, so remember that you need to use 2 blocks, 2 small blocks, to represent one value, one digit, or to represent 1%. So 1% in essence is equal to 2 small blocks. Okay, so what I'm trying to say is that these 2 blocks represent 1%. Okay, so make sure that you've got that down. You don't make a mistake when you do the plotting. So in this case, we have 82% or 81% right there. So we need to go all the way across to this side and mark down the 81% here. You can remove the ruler now and properly mark your 81% there. And your next point would be 73%. So and that will be against a discharge value of 0.035. So let's get our ruler out again. Okay, let's see. Let's get it. aligned. Scroll up, it has to be 73%. Let's go to 73. So here's our 70. 73 has to be, so it's 3%, so it's 6 small blocks. So it's 1, 2, so it's going to be somewhere here. So it's going to be that one there. And we can plot. Then our second last one is the 55 meters, or 55% rather, 55%. So let's use our ruler again and move on to our next discharge point, which in this case will be 0.045. This one right here, this guy. Okay, so let's scroll up and let's go to our second point, which has a percentage value of 55. So let's go down here. So 55 will sit right here. So we have to move across to our discharge point. So this will be our 55% mark or plot. Let's turn off the ruler. Let's get a good mark on there, and we're almost done. Then we go to the last one. Let's turn on our ruler again. The next one is going to be the 0.05. Let's just turn our ruler to 90. And let's go to our last plot point. Make sure it's 0.055. It's here. And your head value that you have to plot is 38 meters. So we have 38 here, 30 here. So 38 would mean 40 minus 4 blocks. So there's 1, there's about 4, so it's going to be somewhere there. So it's going to be somewhere here. Turn off the ruler, and that's going to be your last point, being at 38 meters of head with a discharge of 0.055. Okay, so now you need to go and create a nice bendy curve, or parabola rather. So this will be a little bit difficult for me to do, but I will try my best. So please, you will have to use your steady hand. I will try and zoom out a bit so that we can connect the dots a bit better. Okay, so the first point, I need to connect this point to this point here. So it will have to look something like this. So we'll have to do it baby steps. So yours will look something like this. However, your lines will be much more straighter than mine. Okay, so this is in essence what you need to have, except that your lines should be straight and smooth. It's a bit difficult to do it on the software that I'm using at the moment. So apologies for that, but remember this is okay. So let's continue. So now we can go and read off these values. So in essence, to make things a little bit easier, I'm gonna write them down on the next page. So to make life a little bit easier, so we're gonna read off these values. So we're gonna read these values. That working point, this working point, and this working point. And we're gonna read off the efficiency values. Alright, so what I'm gonna try and do is I'm gonna add another screen here to help us. Okay, so we have a block now here where we can take the readings that we've plotted. So we need to take these readings, the working points. So for point A, so in each case we'll have a value for a working point for question 1 or 6.1 rather, and for each case for each question we'll have a head value, a discharge value, and an efficiency value. So I'll try and explain as we go along how will you read these values from your graph. Okay, so first of all you're going to need a ruler to read off these values. So let's start with the first one being our head value for pump A. So remember, this is for pump 1. So let's do pump 1. Let's do it in black. Okay, so let's do that. So what's going to be our head value for, well, let's start with the Q values rather. So we'll have QW, so this is for 6.1. Well, question 6.1. So our QW there will be equal to 0.042. So how do I get that? So it's by simply taking my ruler, rotating it, to about 90, and then looking at my duty point, which I have here. This point right there. Okay. So if we go and look at it, it gives us a value of 0.42. Let's switch off the ruler, and that will give us a value of 0.042 meters cubed per second. And what will our H value be? HW for 6.1. So this is for one pump. Let's go and see what will it give us. So let's use our ruler again. We go down, we'll see that it gives us a value of about 39 meters. Okay, and what will our efficiency be? So what you simply need to do is you need to take your ruler again, rotate it 90, connect it to that working point, So then you'll simply go and read off. So you'll move all the way up to where your efficiency curve lies. Which will sit somewhere here. And if we turn our ruler horizontally, we can go and read off the efficiency. So remember, it's where it crosses with the efficiency line. Remember, mine is not entirely correct. But you should get around 62. That's 61, that's 62. So if you plot it correctly, you should have gotten an efficiency of 62%. Okay. So let's remove the ruler and add that to our data. So our efficiency is now sitting at 62%. Okay, let's do our second one. So now we're going to use for the parallel pump, 6.2. So let's do 6.2 where we have our parallel pumps. So again, we will have a QW in meters cubed per second. We'll have an HW that will read off in meters, and again we'll have efficiency in percentage. So let's go and read off those values. So this one you have to be careful. So let's get our ruler out. And go to our working point. That's more or less where the working point is. So we can see from it, this is going to be our point here. That's our working point. Right here. This here. This point here. Okay. So let's see what's the head value that we have, and let's see what the discharge value that we can read off from this working point or duty point. So if we look closely, it should lie somewhere close to 55. So if you plot it correctly, yours should have ended up at around 55 meters. For the head value, and then the discharge, we rotate our ruler, you should get something like 0.055. Okay, so let's write in those values. So we know that H will sit around 555 meters and our Q will sit around 0.055 meters cubed per second. Okay, and what is our efficiency? Now this is where the tricky part comes in. So we've read off a value of 0.055. So we need to take half of that. Because remember, you've got the discharge of both pumps. That's what you've read off now. You've read off the value for two pumps. So, but you need the efficiency value for one pump. So let's do that. So what you'll do is you'll take the efficiency value, the discharge value rather, of 0.055 divided by 2, and you'll get 0.0275. So what you'll get here is, once you've divided it, you'll get a value here of 0.0275. Okay, and that's the value that you're going to have to use to read off your efficiency. So let's put on our ruler again. Let's rotate it 90. And let's see, where is 0.0275? Okay, so now we need to go and read our efficiency value. So we had to take that 0.055, this value 0.055, and divide it by 2. So we had to take this value and divide it by 2, and we get 0.0275. So why, if you had 3 pumps in parallel, you would have taken this value divided by 3, for example. So, but in this case, we only have 2 pumps in parallel, therefore we only divide by 2. So this will become 0.055 divided by 2, and it will give us 0.0275. So we have to go and read the efficiency for that discharge value. So let's turn on our ruler, turn it to 90. And then let's find our horizontal axis value, which is 0.0275. So that one is 0.05 there, 0.025, 0.026, 0.027. So it's more or less this one here. Then we can scroll up and we can go and read off the efficiency. So it's going to move all the way from this line here, all the way up. That's for our parallel setup here. So we've taken the 0.055 divided by 2. And now we're just going to read off what is the efficiency. So this is where it lies. Let's rotate our ruler. More or less to that point. Let's zoom out a bit. Go and check what is the efficiency value, and as you can see, it's more or less 80%. I had to go and mark this all the way across. We'd see that we get a more or less 80%. We can simply go and write down here 80%. move on to our next one. Okay, and our next one would be the pumps in series 6.3, where we have our QW, which is our working point for the pumps in series, measured in meters cubed per second. Let's just get the ruler out of the way. Meters cubed per second. Then we have our HW in meters. And we have our efficiency as well in percentage. Okay, so let's go and read off the values. So that we have our working point right here. This is our working point that we're going to have to read off. So let's go and switch on our ruler so we can read off these values. So let's turn our ruler to 90. That's about 90. Let's go to our duty point. And we've got our ruler set. So now we can simply go and see where we end up with our values, our discharge value. So here you can clearly see it's going to end up being 0.05. Look at this value here. It's going to be 0.051. And what is our head value going to be? So let's simply rotate our ruler to 90 or 0 degrees. That should be 0 degrees. Then we can simply read off what is our head value going to be like. And our head value will be that 50. Let's just get the ruler out of the way so we can clearly see that it's 50. So that's going to be 50 meters of head. But now what's the efficiency? This will be simple. So it's not as difficult as the parallel setup. The series setup is similar to the Onepump plot we had earlier. So again, you have your 90. You go to your pumps in series, the duty point, and then you'll simply draw up from your duty point. You'll draw a line straight up towards your efficiency curve again. So because mine is not perfect, you should get, if you've plotted correctly, you should get about 40%. The efficiency should lie at around 40%. So meaning it should have been here. That should have been your plot point there, your intersection between the intersection to your efficiency curve. So that should sit at 40%. So let's get the ruler out of the way. So here you should have gotten about 40%. So these are the values that you should have gotten from your graph paper. And now you simply need to go and calculate the power required. So we'll do that on the next page. Okay, so now we're on the next page and we've got our values written down. Now we have to calculate the power. So the formula that we'll use is P is equals to rho G HQ divided by the efficiency. Okay, so remember your efficiency, the efficiency values need to be in decimal values, not percentage values. Okay, so let's do the first one. So the power will be equal to a density of 1000 for the water times 9.81 times a head value of 39 times a discharge of 0.042 divided by our efficiency of 0.62, and that will give us the power. So let's quickly calculate that. And that should give you 25,917.387 watts. Okay. And that should give you 25,917.387 watts. So that's a point there, 0.387. Now the next one is for the pumps in parallel. So here again we'll use the same formula where power is equals to the density times gravity times Q, but Q divided by 2 here times H divided by the efficiency. Okay, and the reason why we're dividing Q here by 2 is because remember we multiplied the Q values by 2. And also when we read off the efficiency value, remember we divided the discharge by 2 and then we read off the efficiency of 80%. So your calculation will look something like this. It will be 1000. So the first power you'll calculate, the power will be for one pump. So it will be 1000 times 9.81 times your Q value, which is the 0.055 divided by 2 times your H value, which is 55. Divided by the efficiency, which is 0.8. So let's quickly do that. It will give us an answer in watts. Just make sure that you write out the watts. It's going to be in watts. So let's quickly calculate that one. And this should give you 18,547.0.031. So now to calculate the total power needed, we're going to take this value times 2. We're going to take the 18,547.031 times 2 because we have 2 pumps, and that will give us a total value of 37,094.063 watts. Okay, now we can do the next one. So here we have the same formula again, where power will be equals to the density times the gravitation times a Q value again, and times H here, this time divided by 2, because we have 2 pumps in series, divided by our efficiency. So again we will have our power being 1000 times 9.81 times our Q value of 0.051 times our H value, which is 50, divided by 2, divided by the efficiency, which is 0.4, and we can calculate the answer in watts. And you should get an answer of 31,269.375. But this is just for one pump. We need to show what's the total power required. So P total is going to be what? It's going to be this 31,269.375 times 2. And that will ultimately give you 62,538.75 watts. And that's how you solve this problem. So another thing that you can look at is, for example, if I asked you which pump would you suggest to the client, for example, then just because of the amount of power used, if you look at the amount of power used by each pump, Let's see this one. That's the total for the 2 pumps in parallel. That's the total for the 1 pump. And this is the total for the 2 pumps in series. So which one uses the least amount of energy? That's obviously the 2 pumps in parallel, which uses 37,000 watts, more or less, 37,000 watts. And if we look at the output it's giving us 0.055 cubes per second, and it's also giving us a head of 55 meters, and it's working at an efficiency of 80%. So it's much better than this one, where we have almost the same discharge and almost the same head, but the efficiency is sitting at 40%. So if you would have to select the best pump layout or pump setup, it would be 6.2 here, because of the power output, the power required. And I hope you've enjoyed this video. Thank you for watching.